Welcome back. I know I promised that episode 6 was the grand finale, but we have episode 7 still for some reason. Um, in particular, we need to make sure that our text functions for working with text as numbers in R um, are still viable and are working with extremely large numbers. And it turns out that they're very close but need one little tweak. So what I'm going to do in this episode is work through the example that you find on the Wikipedia page for RSA cryptosystem. I'm going to use the same numbers here and do a few messages, but I'm not really going to explain much of why I'm behind the math at this point. Okay, so run line 4 if you haven't installed GMP already, and then of course the first time you open R you should be running line 5. And that'll install what's called the General Multiple Precision package. It is useful for working with extremely large numbers. Um, and now you might think that we're doing these kind of toy examples, from the Wikipedia numbers, which are much smaller, and they are. But even when you're doing that, some of the numbers that you calculate in the process of doing the encryption and decryption get unexpectedly large. So if you're doing any sort of RSA at all, you need to be working with a package like GMP. Okay, n is defined as the product of these two prime numbers that we've chosen, p and q. Since p and q are prime, their totient simplify, and so the totient of n works out to be this. And so I guess I should be executing these. To choose either rules for that, you need to look up and be careful about. D is the modular multiplicative inverse. I'm going to talk about this one a bit more in a moment because it's not obvious how to find it. E and D should have this property that implies that the totient, if you take the product of the E and D and then mod of the totient of n, you have 1. So what we're going to do is work with this function that gives us the greatest common divisor, and also in addition to that it does what's called the extended Euclidean algorithm, and gives us particular coefficients that allow us to solve for D, which we need. So what this is doing here, the first number is the greatest common divisor, and then you get the two Bezout coefficients. Now, you can use them in this case in a particular way like this. You just add the totient together, and now what are the square brackets to? They're picking out the 367, which is the one that we want. We add these together, and lo and behold, 2053, just like we had above. Now you need to be careful when using this GCDEX function, because if you put in the numbers in the opposite order, you'll notice that you get the same numbers back, but they don't come back in the same sequence. So you need to pay attention to how you're entering those two numbers to make sure that you're getting back the one that you want. Okay, so now to get our public key, you can think of C as our cipher message. It's some function of our original message M, as well as some of the other numbers that we've been talking about. So just to start with the example they have on the website, we'll put M to 65. This is the function we wrote in an earlier episode, I think 2 or 3. In case we forgot our ASCII, 65 is just capital A. Now to encrypt, all we need to do is this one little thing here. We need to take some value that goes in the first spot, x, some value that goes in the second spot, y. We raise x to the y and do mod n. And that's it. Now we've got a number which has been encrypted, 2790. It bears no obvious relationship to 65, and that makes it difficult for interceptors to work backwards. Let's say we need to decrypt. It's very similar, but you notice now that we work with D, and we again use this same function. And look at that, we got 65 back. One very nice feature of GMP is that it vectorizes, which means that we're going to be able to do more than one at a time, one character that is. So we've reset our message. Let's say our ASCII is a bit fuzzy. We could do a command like this, and in fact, it is my first name, or an abbreviation thereof. So now we've got this new message we can encrypt and we can decrypt. Look at that, we're getting back the same integers we started with, exactly what we want. Okay, now you might be wondering, we wrote all these great functions earlier episodes, but how exactly we're going to make them play nice with these extremely large integers. There's one little thing we have to bear in mind. It turns out that since GMP works by converting, let me put it a different way. The GMP package works by treating these really long integers as text of some sort. So we're just going to need to use our as character and as numeric to get what we want, basically. So I've written this little function here, format text, which basically all it does, format text.gmp, and basically all it does is call the format text function that we already have. And I've set it by default to clean the text, and I've set it by default to convert to ASCII, but to leave it in decimal as opposed to binary. And as we talked in earlier episodes, we want to display this ASCII code as compactly as possible, so we want to use numbers under 100. So if we subtract 23 off of the top, that'll do that. That'll keep the largest ASCII code lowercase z. It'll map that to 99, making it only 2 digits. Okay. And same on the way back, that we're going to use numbers to text, which we already wrote. We're going to correct for that same offset, which again we can change as long as we're consistent in both places. The false right here, that's the binary. You hit tab, you see what the options are. The second argument is whether we want binary or not. And I'm going to put that to false because we really are just working with decimal at this point. Now you can easily switch to working with binary by changing those things. Okay. Okay, $64,000 question. Does R play nice with the other letters? This is a messy text with these question marks and everything else. Now, what do we have? We have a bunch of numbers under 100, just like what we want. And again, we could always, if we needed to, we could use paste message collapse equals nothing in between it, and that would give us this big message like this that looks super hard to decrypt. And so did I run this already? And now we need to decrypt it in the same fashion. Look at that. Does R play nice with the other letters? Now, of course, we've written our initial function to make everything lowercase, and to in addition, get rid of spaces and extraneous characters. So you could go back to the original format text function if that's not what you wanted. But in encryption, of course, we want to remove anything that could be identifying information. So that's actually just what we want. And so just to show it once more. Okay. Hope you all learned something useful.